everyone, my name's Karolina and I wanted to talk about pre-treatment methods in enamel and the age-old question, to treat or not to treat. So I'm sure we have all come across a problem when you drill a bunch of animal teeth and then think, should I or should I not treat it? What acid do I use? What the concentration of the acid? How long do I leave it in? And I've definitely had this problem. This is the whole reason why we came up with this. And then you go on, start reading some papers, and you see that everyone is doing something slightly different. And you just end up picking something that kind of just seems okay. But it is really important to think about why and how we do it. So why does it matter? So we all here care about the isotope values and that they are real and actually accurate to the original signal that we get. And treatment can introduce uncertainties and changes in isotope values that could be negligent, 0.5 per mil, 1 per mil, and more. And when it comes to interpretation, 1 per mil difference can be a difference between interpreting an animal or a human as a C4 consumer or a mixed consumer, or if an animal was living under a canopy or in an open field. So it's really important that our data and our values are actually accurate. So to kind of set up a bit of the history of the research, so as Julia Leethorpe talked yesterday, the history into the diagenetic changes in enamel and treatment options date back to the 80s and 90s, but the more recent discussion is shifting more to conservative and less harsh treatment options to ensure that the structural integrity of the sample stays. However, there's also been an increase in discussions about the need for treatment altogether, because the treatment can significantly affect the isotope values, thus potentially altering the original signal. But more importantly, we don't really know what we are removing. Are we removing the supposed contamination in the enamel, or are we removing something that's structural and is important that we don't remove? There comes some methodological issues that we have in the literature at the moment. While it is pretty much agreed that we should use acetic acid, there's still no consensus whether it should be buffered or unbuffered. People use both. There is some evidence suggesting that buffered acetic acid results in less sample loss. However, it's not been fully replicated. Another big question, bleach. While it is usually used as a first step to remove organics from the enamel, which in archaeological enamel, it is questionable how much there is of it. But it is also, there's several studies that show that using bleach can facilitate absorption of exogenous carbon, potentially from the atmospheric carbon. And it is a big problem if we want to preserve the values. Then, how long do you treat it? It is just as important as what type of treatment you use. There are several studies that investigate the length of treatment in bone carbonate. Before enamel carbonate, there isn't a recent up-to-date study. And even then, some treat for 15 minutes, some 4 hours, overnight, 24 hours. There's a huge array of time that people treat it. And the most current recommendation seems to be, let's do a short leech that's less than 8 hours, but that is very vague and doesn't help a person that maybe is not necessarily as versed in the all the chemical nuances of it. And lastly, what are the burial conditions of the material? Because that could have a significant impact on the diagenetic alterations that happen, as well as the sort of contamination that could affect the sample. and it hasn't really been systematically addressed, and we are kind of starting to try to tackle that idea. And again, why do any of these questions matter? It is carbon and oxygen enamel analysis of isotope analysis is very commonly used, as you can see from all the posters. Almost half of the posters are using sequential carbon oxygen analysis. And it's important that we use consistent lab protocols so that the material and all the published data is comparable with each other. But also we need to kind of understand what we are actually removing, because it's still a bit under the question. And lastly, because it has been shown that the treatment does affect the values, and now as we're going to a more high resolution questions, even small differences in values post-treatment can make big impacts on our interpretations. So this is really, really important. So what did we do? So we analyzed 3 archaeological sites and 2 modern sites with 10 individual teeth each, with 5 being Ovocapra and 5 being Boss. We did bulk sampling from the whole crown to the root where possible. And these are the sites that we picked. So the first site is Tel Handakuk South in Jordan. It's an early Bronze Age site from the highlands of Jordan. And during the excavation, it was noted that both bone and teeth were crusted with these calcareous concretions, which definitely could suggest some contamination or some sort of diagenetic alterations that could happen. The second site is Wadi Faynan in Jordan. It is an early Neolithic site in the arid Wadi Faynan. And the teeth from this side were highly fragmented, super brittle, enamel was extremely thin. Then we have Oldenburg, which is a Middle Neolithic funnel beaker site from northern Germany. The picture is not from the side, but to kind of show it is it is a waterlogged site because it is on the coast of the Baltic. Thus, a lot of the teeth were highly discolored, brown, and even black in some parts, which could suggest that something strange is happening. And then we also had some modern samples, so sheep from Mongolian steppe and Olphin cattle, which were modern. And this is kind of like our test, control. What did we do? So as a pre-screening, we used ATR, FTIR, just to kind of, for people that are unfamiliar with that. And we tested the samples prior to treatment to look at any diagenesis, and also post-treatment to assess any changes done by the acid treatment. And on the right, you can see all of the parameters that we have used, as well as their corresponding peaks on the FTIR spectrum. Next, we have put the ground powder under a bunch of different treatments. The buffered, unbuffered acetic, different times. We also included bleach, as well as a combined method that some people use. We still don't have some of the results from the lower treatment protocols, so we're just going to present what we have so far. And obviously, mass spectrometry and FTIR post-treatment was also done. So kind of results. In the table, you can see all of the untreated teeth and what parameters that they have failed. Tel Handakuk South and Oldenburg, seen on the bottom, are the ones that failed the most parameters, as we kind of expected based on the visual observations. And WF16, which is the top right didn't fail anything, and that's the highly fragmented samples. Interestingly, 2 of the modern samples failed the API parameter, which was surprising to all of us. However, when you look at the examples of the spectra, the 1540 peak, which is in the API parameter, is very small and kind of hard to see even in the good samples. So I'm not sure how maybe great or useful it is to use it. But yeah, some examples of how our spectra use looked like. Then I think what's really important when you talk about conservation and using as little material as possible, and then you want to lose as little material as possible, what we've found that pretty much all of the treatments, regardless of if it's buffered, unbuffered, or the time length, the average sample loss was about 22 to 25%, with the exception of bleach, which was surprising because we thought that there would be more sample loss with longer treatments. And it has been shown, some people have talked that buffered would have less sample loss than the unbuffered. We did not replicate that. And the reason for the bleached sample loss being smaller could be the potential of absorption of exogenous carbonate, and it's rather not the less loss, but just with absorbing something and losing the same as the others. Then it's a very big graph, are the actual results. So what we did is we took the shift for each treatment, colored in different colors, and compared it to the untreated value. And this is the graph from the modern material. And in theory, there shouldn't really be any contamination or diagenesis going on in these samples. But there's a noted shift in both carbon and oxygen in both the Mongolian sheep and the Olphin cattle, which is very interesting. If we look at the talhandicoxal, which is the teeth with the calcareous concretions, there is considerably higher shifts compared to the modern, but there's still a huge variation between the treatments and between individual teeth and even within the teeth. And there doesn't seem to be kind of correlation between the FCA parameters and the changes. So it's all a bit strange. Then Wadifeinan, which is the side that passed all of the FTAR parameters, and there is still some considerable changes happening, which, maybe we didn't expect. And on the bottom especially, you can see that the bleach one really changed the oxygen values quite a lot. And for the oxygen as well, the values go both up and down, which is extremely concerning. And lastly, the Oldenburg, the waterlogged brown teeth. And again, this is arguably the most diagenetically altered group of samples based on FTAR. But there's still such a huge variation, and there's no really a reason that we can kind of think of. And this is the summary, and interestingly, Oldenburg seems to be the most kind of changed during but as you can see from the shifts, the average shifts for the carbon were actually lowest in Oldenburg, even though they looked the most diagenically altered or poorly preserved. What is very interesting is that when you run the FTAR of the treated samples, we had a few samples that passed prior to treatment. They passed all of the parameters after treatment, like the THS1. There were some that failed the same parameters prior and after treatment, which is THS6, but most of the samples, especially the Wadi Feynan and the Oldenburg samples, they all go worse after treatment. They start, and especially like the worst example is WF4, which passed all of the parameters prior and then failed a bunch after. So this could suggest that the treatment is significantly affecting the crystalline the matrix and the structure of the enamel, maybe in a way that we don't really want it to. And here's just some two examples of the whole spectra from untreated all the way to the harsher, longer treatments. And there doesn't seem to be the correlation between the worsening of FTIR and the shift of carbon and oxygen values. And the same in the Oldenburg 9 sample as well. So kind of what are the outcomes, the takeaways from all of this results that we have so far? Is that maybe FTIR doesn't detect the changes in enamel that affect carbon and oxygen values, because there didn't seem to be a correlation between the failed parameters and changes in carbon and oxygen values post-treatment. In fact, the FTIR spectra of treated samples suggests that there are alterations happening during the treatment, which could suggest that treatment is affecting the structural carbonate instead of maybe contamination, or maybe there isn't contamination, which I think we should all keep in mind when we choose our methods. Another thing is, for the most part, the shifts in isotope values in most samples weren't that great. They were equal or less to 0.5 per mil, and could be within the range of biological variation and could not really affect your interpretation. Like 0.5 per mil is maybe not that significant for a lot of the questions that we have. However, the large variability in isotopic shifts and the directionality of it raises concerns, because if you have taken a bunch of teeth from your site and some post-treatment are shifted 0.5 positively, the others are shifted 0.5 negatively, you have a 1 per mil difference, and you might interpret the two samples as having some different practices being done or different environments. But we don't know if the shift is because of the contamination or something that we remove from the carbonate, the structural carbonate. So the base value, the untreated value, is the same. So where does the difference actually come from? And that's a kind of a problem. And when it comes to the burial environment, our results don't really show a clear connection between the burial environment and the carbon and oxygen values, apart from maybe being cautious of waterlogged material, because that seemed to be the most unpredictable one. However, we can also note that there's a large variation in the shifts within a single site, which could suggest that there is a micro variation in burial environment with each individual context that the teeth are found in, rather than the general site environmental context. Another reason for that could be that the acid is affecting individual teeth differently and maybe even unpredictably. So that's kind of what we've gotten so far. We have more results coming soon, and I think to some people this might be a bit discouraging, but I think it's making some like important progress on how we think about methodology, and I would be very happy to like talk to people and to hear their ideas, what they think about all of this data, because it is a lot of data and it's showing very kind of slightly strange things. And yeah, so thank you.